hope you guys
Sorry.
appreciate the significance of, is that these guys should be hypercalar. And, you know, somehow I came into this field through a route such that hypercalar things didn't seem that special to me, you know, like lots of things are hypercalar. But I've come to appreciate like, oh, it's actually pretty hard to construct hypercalar manifolds. And so if you like this style of geometry, of the kind of interplay of complex and symplectic, if nothing else, the idea of, well, we may have a new interesting source of hypercalar manifolds should be itself kind of something worth paying some attention to. Now, this may contradict what I just said. The other thing that's interesting about them is we know that in many special cases, we actually get examples we already understand, but get a new light on. And actually, maybe this is kind of, you know, if you take nothing else away from the talk, this is sort of the important idea that even examples that we knew about before, when we think about them as Coulomb branches, we learn something new. And part of how we learn that is Coulomb branches are surprisingly enough kind of more combinatorial than Higgs branches, which I'll talk about in a moment, which is kind of a more established way of getting hypercalar manifolds out of these theories. So those are hypercalar quotients. That's kind of the main construction that people use to construct examples of hypercalar manifolds. And those are very nice. We've been studying them for a long time. And then these Coulomb branches kind of came along and said, well, actually, we're as important as the Higgs branches. And in some ways, we're easier to study. All right, so what I'm going to try to cover in this talk is what I know about mirror symmetry for these as kind of a route into thinking more generally about them.
So this mirror symmetry is between, within, it's always in, it's a duality between different Coulomb branches, not...
Okay, so I'm going to be talking about 2D mirror symmetry for these guys. So there's also a 3D mirror symmetry, and this is a potentially confusing point. So so what does 2D mirror symmetry mean? It means that there are theories, 2D theories, that come from sigma models into Kähler manifolds or different generalizations of those, which give you, where two different looking Kähler manifolds can give you the same theory, but with the supersymmetry acting on it in a different way.
Right.
Excuse me. There are also three-dimensional theories, which you can think of as sigma models into hypercalar manifolds, where the same theory with different supersymmetry will show up, giving you the same 3D theory. I'm doing something weirder than that. I'm taking my 3D theory, kind of torturing it a bit. I'm getting a Kähler manifold out of that, actually a hypercalar manifold. And then I'm looking at the 2D sigma model into that hypercalar manifold. And from a physical perspective, this is a little unnatural, but it does come up. I've been thinking about it a lot recently, kind of in connection with this work of Mina Aganagic about knot homology, which kind of actually gives a kind of physical reason that you would be considering this 2D sigma model into the Coulomb branch of the 3D theory, but it's kind of mixing quantum field theories in a slightly strange way.
All right.
All right. Okay, so Coulomb branch, this is a kind of general notion in physics. I should mention here, branch is really just sort of the physicist word for component of an algebraic variety. So the physicists sort of think, oh, well, there's this kind of space of vacua, which is very singular. You could think of it as an algebraic variety, and it would have a bunch of components. And there's one special one called the Coulomb branch. All right. But this is a notion that shows up many places in physics. So there are lots of different kinds of theories that have different Coulomb branches with different kinds of structure. So the specific case we're considering is So as I said, 3D, n equals 4 supersymmetric. And it's even a special kind of those theories. There are other kinds of theories with that dimension and supersymmetry that we don't understand as well. It's specifically the sigma model into a quaternionic vector space. So this is a vector space that already has a hyperkähler structure. You need that for the n equals 4 supersymmetry. And I gauge that by the action of a compact group G. So there's sort of different ways you can think about this guy. Sorry, what was that?
Excuse me, do you always assume this quaternionic space to be cotangent type?
I am only going to talk about cotangent type in this talk. So
Okay.
there is recent work about non-cotangent type, which we don't understand as well. That's kind of a very new story, and one that I hope to understand better eventually, but I haven't gotten around to it. So
Thank you.
You know, some of the things I will say will apply in that case, but so that, you know, hopefully in a year or two, I can give that talk where I include the ones that aren't cotangent type. All right. So if you've encountered this theory, you're much more likely to have heard about it in the context of this Higgs branch, which mathematicians usually call hyperkähler reduction. So this means that I take this T star of n, I have a hyperkähler moment map. So, right, this guy, it has 3 complex structures. I choose, given by I, J, and K in the quaternions. I choose a metric that's compatible with all of them. That gives me 3 symplectic forms, which I kind of can package as mu R is the usual Kähler form for the obvious complex structure on this guy and my chosen metric. Whereas mu C comes from thinking of T star n as a cotangent bundle and taking the obvious complex symplectic structure on T star of n. And of course, implicitly, that's corresponding to J and K as complex structures on the quaternions. All right. So when I do this, right, I'm dividing out by 3 different moment maps, taking levels for 3 different moment maps, and then dividing out by this compact group. And the result is hyperkähler. So it was a theorem of Hitchen, Karlrede, Lindström, and Rocek that as long as I choose a regular value of the moment map, this quotient is smooth and hyperkähler. So you should think of a Coulomb branch as a dual way of looking at the same theory, but extracting different information from it, which hopefully will be in the form of a hyperkähler manifold. Unfortunately, at the moment, there's no kind of uniform proof that there are hyperkähler metrics on smooth Coulomb branches, or what conditions you need to get a hyperkähler metric. There are many cases which we can also write as hyperkähler quotients, and so we know that those have hyperkähler metrics. But this is one of these things that's kind of a big hole in the theory of where are the hyperkähler metrics going to come from. All right, but we're still in a big improvement over the literature from before 2015, which is, if you looked at the literature before that, they would say, okay, well, there's this thing called the Coulomb branch. And what it kind of is, so there's a couple of ways to think about this. You can kind of most compactly write it as this cotangent bundle of the Langland's dual of the torus of G. So here, T sub G is maximal torus. I'll just remind you, G is compact. So this is an actual product of S1s. I complexify it. I take its Langland's dual, and I take the cotangent bundle of that. Of course, that's the same as taking the Langland's dual of the complexified Langland's dual, and then the cotangent bundle is trivial. So it's actually just the product with this Lie algebra the complexification of the Lie algebra of the torus, and I mod out by the bottom. And the physicists say, oh, well, that's kind of right. If you just sort of analyze the field theory naively, that's what the field theory is kind of suggesting. But that's a classical field theory. You've got to do it in a quantum way. There are quantum corrections to the multiplication of functions on this guy, which are going to change the metric and the topology. So actually, there's this little squiggly equal sign. This is actually only birationally true. The Coulomb branch is birational to this guy in kind of a canonical way, but it's not actually isomorphic to it as an algebraic variety. All right, well, so when I came into this theory, we were kind of stuck there. Basically, physicists said, well, there's some quantum corrections. There are some cases where we can use some string theory to get around this and rewrite this Coulomb branch in some other way and do the calculation. But they had no good kind of uniform explanation of what the Coulomb branch was. And then there was this really beautiful work of Braverman, Finkelberg, and Nakajima, which solved this problem, which told us exactly how to understand the quantum corrections in the cotangent case, right? So part of why I can't say very much about the non-cotangent cases. It took another 5 or 6 years. There's recent work of Telemann and of Braverman, Dillon, Travkin, Finkelberg, and Raskin, which cover the non-cotangent cases, but that's from like the past year. All right. And unfortunately, the way they do this is a little bit implicit. It involves the geometry of the affine Grassmannian. And it's sort of a beautiful picture if you know this kind of yoga of geometric representation theory. It's kind of an interesting analog of like the Springer resolution. So it's a really nice picture, but it's kind of hard to work with. So I'm not going to try to explicitly describe it. You guys are free to read the paper. I'm happy to talk about it. So I'm just going to be a little more vague. But you can sort of, unpack their definition. What it tells you is sort of, you start with what the physicist told you was the classical guy, and then you sort of modify the geometry of it. So how do you modify the geometry of it? Well, this is a fibration over the complexified torus mod W. So for every point in the complexified torus, I can look at how that acts on the representation. And of course, since everything's up to conjugation, well, I know how it acts up to conjugation. I can look at its eigenvalues. And as long as the eigenvalues of this guy on T star n and on the adjoint representation are all non-zero, the fiber stays the same. It just stays the Langland's dual of TC.
So the fiber is a torus, right?
Yeah, the fiber is, it's the Langland's dual of the torus of the group. Now, so what happens if some of these are zero? If I have some zero eigenvalues acting on T star of n,
But the Langlands,
what I do is I collapse some of the directions in the torus. I'm sorry, was that a question?
The Langlands dual of the torus of the group is just the torus, right? Just the classical torus over C. Is this correct?
Not canonically.
It's just GM times GM in a sense, like the finite product of,
yes, they
GMs.
are isomorphic, but they're not canonically isomorphic. So you'll confuse yourself horribly if you start doing one instead of the other. Like characters are not co-characters. And in this story, like you have to keep track of them. Mm-hmm. Like if you don't do that, you're going to start writing like, you're going to like not put in Langland's duals you're supposed to put in, or not put in ones. Yeah, like you'll get all mixed up. So you're absolutely right. Like topologically, or even like as a group, it is just a big product of GMs. But it's not canonically, right? I have to make some choice to get that isomorphism to a product of GMs. And I shouldn't do that. Like, I'll just get myself mixed up if I'm not
Okay,
careful.
okay. Thank you. Thank you. Okay.
So for example, right, like what's going to happen is if I have some zero eigenvalues, I'm going to collapse some directions in this Langlands dual torus, right? And remembering it's the Langlands dual torus tells me, oh, well, how do I find directions in this? They come from characters, not co-characters, right? They come from weights of the representation. So it's exactly, I look at the weights that X vanishes on, and I collapse those directions in the torus, right? And if I had switched Langlands dual, if I hadn't put that Langlands dual there, I wouldn't have a direction corresponding to a weight. I would have a function. Yeah. All right. I'm going to be a little more vague about this, but if I have zero eigenvalues in the adjoint representation, so a root vanishes, then I also have to do something a little complicated. The geometry, which you can think of as a kind of blow up and then removing a hyperplane. So I think this is sort of clearer if we talk about some examples. So if we talk about G equals S1, that's kind of the simplest example we can have. If we want to make it really simple, we take n equals 0. So this means that there's never a zero eigenvalue. My fibers always C star, and I get just this picture. And I've got sort of my copy of C down here, and then I have copies of C star over it, which is a little hard to draw, so I'm drawing the unit circles in those. On the other hand, if I bring in some matter, this representation N is called matter, well, what's going to happen? Now I'm going to have a point where my eigenvalue vanishes. So over almost all of these points, the circles stay the same. But then there's a point where it vanishes. And the way to think about this is instead of having these uniformly sized circles, I have some shrinking ones. It shrinks down to a point and then it starts expanding again. So I get this kind of cone. And this is actually, I'm looking at C2 mapping to C via the map XY maps to X times Y. Right, so if the product is non-zero, then I get a copy of C star as the fiber, and then over 0, things degenerate, and I get 2 lines instead of that copy of C star. All right. More generally, well, it's going to be kind of hard to draw the difference, but if I start adding in more copies of the same representation, well, now my weight is vanishing to a higher order. And that's actually reflected in the geometry, that I have more vanishing weights. So instead of just getting C2, I get C2 mod a cyclic group acting symplectically. Whoops. So it's acting via the matrix. Here's e to the 2 pi I over n. Here's e to the minus 2 pi I over n. Up to conjugacy, this is the only action that preserves the symplectic form on C2. So I feel the need to write it down, but actually there's only one possible action that would keep the symplectic form. Now, as I said, if I have a vanishing root, life is a little more complicated. But let's talk about at least one example. So if G is SL2 and n equals 0, so somehow all the other cases are kind of somehow locally this guy, but maybe combining with this collapsing of the fiber and sort of along different directions corresponding to the different roots. So what this guy is it's the balanced horizontal Hilbert scheme. So what does that mean? I could look at C2 and I could look at its Hilbert scheme for 2 points. Hilb 2 of C2. So that means the ideals in the polynomial ring with 2 variables such that the quotient by the ideal is 2-dimensional. So one way to do that is to have the structure sheaf of two different points, and then the points can come together and I have some choices. Right? So that's a resolution of singularities of C2. Balance just means I look at this and I say, oh, there's a dumb direction in here. This whole map has a factor of C star coming from, I can translate everything simultaneously. So balanced means I get rid of that by making everything average to 0. The average of the points in the support is 0, 0. And then as I said, so that's the blow up. I have to remove a divisor. And the divisor is that I'm making it the horizontal Hilbert scheme. So when I take my map of C2, where I project out one of the coordinates, I actually have to map isomorphically to a subscheme of C. And so I can't have two distinct points that project to the same spot. And I also can't have a fat point where the fatness points along the vertical line. So I'm removing a divisor, which is all the stuff that sort of where things are lined up along a vertical line. All right. So I'm still getting some extra stuff coming from the fact that I can have my point at 0, 0, and I can have fat points pointing in lots of different directions as long as they don't point vertically. Right? So the important thing about sort of the Hilbert scheme is when two points come together, I remember the slope that they came together on, right? I don't just end up with like 2 points sitting together. I end up with 2 points and a slope, and I'm just excluding that slope being vertical.
May I can have a question just to understand some. So to get the setting. So for the first case, you have G is as 1 and N 0. What does it mean? Do you have some just a trivial representation on C, or what do you say?
Yeah, the trivial representation on the trivial vector space.
On a trivial vector space, a 0 vector. Okay, okay.
I mean,
And then
it actually wouldn't change anything. The trivial representation on any vector space has the same Coulomb branch, but
the second one is, I know that's just rotation, I guess. And
sorry.
But for the
Yes.
third one, which representation do you take? You have
It's rotation on every coordinate.
Rotation on every coordinate.
Yeah.
Okay. Okay.
Right. I
And
mean, I think of S1 as a subgroup of C star. So when I say usual action, I mean thinking of S1 as like U1.
yes. Okay. And in the third case, you have it on every of any direct sum, and you have this rotation action of G. Okay.
Yeah.
Right. Okay. And how do you get Coulomb then? The Coulomb branch? Sorry if I can.
Well, you go and read BFN's paper.
Oh, you have to. Oh, okay, that's a bit more. Okay.
Yeah.
Okay. No,
So somehow I think you could give a definition, which was basically these examples I just told you and a slightly more general SL2 example, and then sort of say, that's what happens in codimension 2, and then you just kind of fill in the rest by chanting Cohen-Macaulay. Like the rest kind of is somehow determined by what happens in codimension 2, but very implicitly. And so it's very hard to like answer algebra geometric questions about what's happening on more singular points if you do it that way.
Okay, thank you. Okay.
Yeah. All right, some examples. So here I helpfully provided also the Higgs branches of these theories. So this is one we already talked about, where U1 acts on Cn plus 1 by the obvious action on every coordinate. And the Coulomb branch there is C2 monocyclic group. The Higgs branch you can work out is T star Pn. So this is basically the usual construction of Pn as a quotient quaternionized. On the other hand, there's kind of a dual example here where, so this U1 to the n, that's the diagonal matrices intersect SLn plus 1. So the n plus 1 by n plus 1 diagonal matrices with determinant 1, which is isomorphic to n copies of GM. But that's, you know, implicitly telling you an action on Cn plus 1. And the Coulomb branch of that guy, I should say I've been talking about the affine guy. So it's the affinization of T star Pn, which is a minimal nilpotent orbit. In n plus 1 by n plus 1 matrices. So it has a resolution by T star Pn. And a few other interesting examples. If I let GLN act on matrices by conjugation and on vectors by left multiplication, then what I get is the symmetric powers of C2, and more generally, I can get symmetric powers of this C2 mod a cyclic group. And this is a little more complicated, but what this is you take n by n minus 1 matrices, n minus 1 by n minus 2 matrices, n minus 2 by times by n minus 3 matrices, and mod out by GLN minus 1, GLN minus 2, GLN minus 3, and like GLN minus 1 is acting by right multiplication here and left multiplication here. And GLN minus 2 is acting by right multiplication here and left multiplication here, etc. This is a little bit strange, but if you've thought about the representation theory of quivers, this has to do with the representation theory of the quiver as a straight line with the dimension vector. Like this. And it turns out that that guy gives you both as the Higgs branch and as the Coulomb branch, the nilpotent cone of n by n matrices. And then one which is very degenerate from the hyperkähler quotient perspective is the trivial representation and an arbitrary group G, the Higgs. This isn't even quite right. It's sort of point mod G, but it's actually like a point with a weird derived structure. Whereas the Coulomb branch is actually the phase space of the Toda system, which you can write in a few other different ways. It's like the universal centralizer amongst regular elements of the Lie algebra, etc. All right, whew. Going pretty slowly. Well, at some point we'll speed up. Okay, so the kind of easiest to understand examples are when G is abelian. In this case, the Coulomb branch is what's called a hypertoric variety. So this has a map to the Lie algebra of the group, since the group is the same as its maximal torus. The generic fiber is the Langland's dual. And then it sort of drops on some subspaces. So right inside this Lie algebra, where the weights of n vanish, defines a hyperplane arrangement. And kind of the more of these hyperplanes I'm on, the lower the dimension of my fiber. And it turns out there's a resolution of this guy, which kind of you should think of as having something to do with pushing these hyperplanes off the origin. And in fact, there are many such resolutions because there are many ways of pushing these guys off the origin. And the thing that has to do with this is there's a real sort of Kähler form that this is the moment map image of the resolution form. So sort of different ways of pushing it up, we give you different complex structures of the resolution. All right, and the way that hypertoric varieties were originally defined was as a hyperkähler quotient. But it's a hyperkähler quotient for a different group. I have to look at my group inside diagonal matrices, take the perp, and do the hyperkähler quotient for that perp, and that will get me the Coulomb range. So for example, right, we talked about these guys, and exactly what's going on here is the matrices that act by scalars, the same scalar in every entry, is perp to the intersection with SLN plus 1. And since those guys are perps to each other, the hyperkähler reduction for one is the Coulomb range for the other, and vice versa.
May I ask a question?
Yeah.
You told at the beginning, a Coulomb branch could be thought about a component, I guess a reducible component of some variety. Is this the same for the Higgs branch? And if so, anyway, which variety are we looking at? For example, in the first example.
I mean, it's called the moduli space of vacua. It's not very rigorously defined, right? So there actually is no clear answer to that question.
That's basically physicists kind of.
Exactly, right. So sort of, yeah, I just wanted to explain where branch came from. But yes, there should actually be some interesting variety that kind of contains both of these guys. But I mean, there's no mathematical construction of it out there.
Okay.
Be an interesting thing to think about.
Okay.
All right. Well, I'll in the time I have left, let me try to say a little bit about mirror symmetry. So how can we do mirror symmetry for these varieties? The only way I know how to do mirror symmetry properly is to compute the Coulomb, the coherent sheaves on one variety, compute the Fukaya category of another variety, and say, oh, hey, look, those are the same. That's the kind of mirror symmetry I'm talking about. And there are other kinds which might be equally interesting, but that's the kind I at least sort of understand, and so that's the kind I'm going to talk about. Well, one thing you might ask is, how are you going to describe the coherent sheaves on one of these varieties? And that actually has a very good answer. So hypertoric varieties have tilting generators. So tilting generator is a vector bundle such that X with that vector bundle induces an equivalence from the derived, that's an important typo, from the derived category of coherent sheaves to the derived category of modules over that algebra, where the algebra is the endomorphisms of the object. And I'll just note here, this implicitly implies that higher x of t are 0.
So it's an honest
higher x of a.
So honest associative algebra, right?
Yes.
Okay.
Yes. Nothing here is a infinity. This is an honest, normal old algebra.
And that is automatic if you're under this I greater vanishing condition.
Yeah.
All right.
All right. And obviously, like this won't happen for all varieties. There are varieties you can prove do not have vector bundles that satisfy these conditions.
Mm-hmm.
But it turns out that hypertoric varieties always do. So I should emphasize here, I'm only talking about the abelian case in this theorem.
I see. That's nice.
So this resolution always carries a tilting generator, and it's actually a very simple tilting generator. It's a sum of line bundles. And how do I construct line bundles on this guy? Well, if I think about it as a quotient, then I can construct line bundles on it by looking at one-dimensional representations of the group I'm quotienting out by. So I look at characters of the group I'm quotienting out by.
Well, but these resolutions, they are non-compact, right? They are smooth. But...
They're very non-compact, yes.
Okay.
Right, right. The largest projective subvarieties are half-dimensional.
Okay. Mm-hmm.
So you should think about something like T star PN, or the unique Krepin resolution of C2 monocyclic group, right?
Mm-hmm.
That's the kind of picture you should think about, that you have the singular guy, and then it's sort of, you resolve and you get a chain of P1s. And those P1s, those are maximal, all the projective subvarieties live inside that chain of P1s, and it's half-dimensional. I should note here, this algebra A is what's called a non-commutative Krepin resolution. All right. I don't have a ton of time, so let me just go through this quickly. There's actually a recipe for constructing these line bundles, which involves taking the torus of your group, cutting it along subtori that correspond to, well, not the vanishing sets, but points where the weights take on particular values. This cuts your torus up into finitely many chambers. You associate a line bundle to each chamber, and the sum of those gives you your tilting bundle. And just as there was sort of some non-uniqueness of resolution that involved pushing hyperplanes off the origin, right? What I'm doing here is I'm taking the subtori defined by the vanishing of the weights, and I'm pushing them off the origin and the torus by translations. And the way I'm doing that is not unique. So it's sort of different choices if I do that can give different algebras A. And there's also kind of, everything is only well-defined up to tensoring with line bundles.
Mm-hmm.
So I'm running pretty low on time. I was planning to do an example of how this works here. So let's talk about the torus inside SL3 acting on C3. So this has 3 weights. And if I sort of draw my torus as a square, right, 2 of the weights I can arrange to vanish horizontally and vertically. And then there's a third one, which vanishes here. And you know, I'm gluing the 2 sides of this. So kind of, you should periodically extend everything you see here. And so if I push off the origin, these guys keep going forever as well. If I push off the origin, well, that just means I move this guy over here. And since I'm supposed to be extending things, there's actually a second copy of this hyperplane over here, because everything I'm drawing here is on the torus. All right. And you see my 3 chambers. So these 3 chambers are supposed to correspond to 3 line bundles. And if you work it out, so I just choose one of the chambers to correspond to a line bundle. Let's say this one corresponds to O. Then what's going to happen is this guy here corresponds to O of 1. And this guy here corresponds to O of 2. And my tilting bundle is O plus O of 1 plus O of 2. And of course, on T star P2, which is what I'm looking at here, this is the only tilting bundle up to tensoring with another line bundle. Every tilting generator has this form. So I knew that was what I had to get. But you can work through other examples like the Krepin resolution of C2 monocyclic group.
But so the derived category of cotangent bundle P2, you taking something supported in P2 or everything?
I'm taking everything. Of course, you can also look at the subcategory of stuff supported on C2. So what's going to happen here is, I mean, I'm going to get a finite, not finite, I'm going to get an infinite dimensional algebra, which is graded with finite dimensional pieces. And so being supported on C2 is being like, finite dimensional and, well, not quite graded, but like, gradable after taking associated graded. So it sort of corresponds to being killed by things of high enough degree.
Okay, but you cannot reconstruct the infinite dimensional one from the finite dimensional one, right? Taking the finite dimensional.
I mean, it depends what you believe. You can, because you have the C star action.
Yeah, so that you need to
So
actually
somehow from the finite dimensional guys, you can construct the formal thing around the origin, and then you can take the C star action and look at the C star finite vectors. This is kind of a standard trick for if you have this contracting C star action, like T star P2 does, then you can sort of only do things in a little neighborhood around C2, P2, and then kind of spread them out using the C star action.
Okay.
Happy to talk about this in more detail, but I'm desperately behind time. So maybe I'll just skip the algebraic presentation. It's nice, that you write down a quiver. It's got some relations that correspond to how chambers meet each other. And I'll just note here, this is sort of a special case of Coulomb, proof of Coulomb that all symplectic resolutions of an affine variety with a contracting C star action, that contracting C star action is important, are all D-equivalent. And the reason they're all D-equivalent is they're all equivalent to the category of modules over some non-commutative Crepin resolution. So you'll note here, like, there are different resolutions of M Coulomb, which are like not isomorphic as complex varieties. They're diffeomorphic, but they have genuinely different complex structures. But you can get tilting generators on all of them by taking the same collection of line bundles. And the endomorphisms of those line bundles aren't going to care which resolution you're on. And so going through that endomorphism gives you a D-equivalence between the two resolutions, an equivalence between the derived categories of modules on them. All right. So you'll note here, I kind of drew two different kinds of pictures. I had a picture that was happening on the torus that represented what happened with this non-commutative resolution. And then I had a picture down in the plane that sort of was telling me about the geometry of this resolution. And this is secretly telling me that if I really want to get the mirror symmetry right, I have to look at multiplicative hypertoric varieties. And again, I'm kind of low on time. The sort of important thing I do here is I replace T star of C with T star of C minus this divisor, and I change the symplectic form on it. That's the sneaky important thing I do. And then I have, instead of a usual moment map, I have a group valued moment map. So the thing that's changed here, this part is the same, but before I had just Zi times Wi, and now I have a group valued map, Zi Wi plus 1. And that lands in the group because I removed this divisor. All right, and this is the formula for the diagonal matrices. For general, I just apply the projection to this, the dual of this subgroup. All right, and now I have a quasi-hyper-Hamiltonian reduction, which is this multiplicative hypertoric variety. And maybe I will sort of skip some of this stuff. This guy has a sort of natural BFN resolution where just everywhere that I took homology in BFN's construction, I take K theory. So the sort of important thing that's happening here is in all these situations where I'm looking, I have a factor of this torus, that has to do with the equivariant cohomology of a point for the torus. And so everywhere I have one of those, I take K theory instead, and that replaces this copy of the Lie algebra with a copy of the group. And so here, instead of a copy of the Lie algebra, I have a copy of the group. And I do all the same stuff locally, but it's all happening over a copy of the group instead of a copy of the Lie algebra. And so, for example, when I drew this picture, I shouldn't have drawn this picture in the plane. I would have drawn the corresponding picture in the group. So things would close up around a torus. Okay, that was a very bad drawing of a torus, but I hope you're getting some vague sense of what's going on. So for example, here, this picture where I took T star of, I took the resolution of C2 mod a cyclic group. Instead, now I get a variety with a chain of P1s that actually closes up, making a closed chain of P1s. This is kind of the picture you should have, that everything I did before. In general, I would have a picture with a bunch of polytopes covering the plane, and I would kind of puff them up to their corresponding toric varieties. And now I do that instead with an arrangement in the torus, which kind of looks exactly like this story, right? I take these chambers, but I do something geometric with them. I take each chamber, I replace it with its corresponding toric variety. I take the cotangent bundles of those and I plumb those together. That's the multiplicative hypertoric variety. All right. And the reason that I want to do this is actually, this is much more symmetric for mirror symmetry. And this cross here tells me I'm taking a multiplicative hypertoric variety. They depend on kind of two parameters. And what should happen is when I swap those parameters, I get a mirror pair. Basically, one of those parameters is kind of telling me the complex structure, and one is telling me the symplectic structure. And there should be an explanation of this in Telemann's framework for mirror symmetry from his ICM address, that he says that having an action of GC corresponds to a map to the Langlands dual of G of the mirror. Hamiltonian reduction corresponds in the mirror to taking a fiber, and the construction of this moment map, this multiplicative hypertoric variety, exactly involves taking the fiber of a holomorphic map to the Langlands dual of the group, which is the complex multiplicative moment map, and then doing Hamiltonian reduction on the fiber. So I'm doing both of these operations twice. And so when I swap, they swap place. All right. And indeed, what we expect would work really does work. If you take the I-Kähler structure, the wrapped Fukaya category of one of these guys, I have this parameter alpha here, but actually the wrapped Fukaya category is independent of alpha, is equivalent to the derived category of coherent sheaves on this multiplicative guy, which I'll note has exactly the same structure, the same line bundles. You like literally just take the same set of characters and take the associated line bundles. It just tweaks the relations in the quiver a little bit to take the multiplicative guy. And I get different resolutions for different alphas, but actually the different choices give me equivalent derived categories. So really somehow what I'm showing is that this Fukaya category matches a non-commutative resolution, and then that non-commutative resolution is de-equivalent to all the commutative ones. And I'll just note here, for alpha chosen correctly, these two guys are hyperkähler rotations of each other. They're literally the same manifold with a hyperkähler structure, and I'm taking, I'm just rotating how I view it. All right, so I have this parameter alpha, which should be kind of unnecessary. It doesn't change what the underlying categories are. But somehow for different alphas, if I'm not careful about this, the identification won't really be canonical. So we match these by looking at this alpha being in being unitary, being in what we called LG. And this does something very special on the Fukaya side. On the Fukaya side, this means we've chosen a hyperkähler structure where we have a Lagrangian skeleton, which is holomorphic. So I was looking at the I Kähler structure to define the Fukaya category. In the J complex structure, this Lagrangian skeleton becomes complex. So there are A, B, A brains. They're Lagrangian in the I and K symplectic structures and holomorphic in the J complex structure. All right. Whenever this happens, I get a T structure on the Fukaya category. On the coherent side, we have our non-commutative resolution of singularities coming from this tilting bundle. And so we get a non-commutative algebra A, which is equivalent to the category of coherent sheaves, the derived category, of course. All right, and this is what I was saying about kind of taking the arrangement down on the torus and turning it into these toric varieties. That's literally exactly the skeleton you want, is that union of toric varieties kind of puffed up from the chambers. All right. So the way everything ultimately goes is we use work of Ganatra Pardon-Shenda to write the RAP Fukaya category as microlocal sheaves on the skeleton we can actually compute with. We do some standard calculations in microlocal sheaves. Really kind of the basic one is on the coordinate cross that allows us to compute the algebra given by kind of natural transformations between the functor of stock on different components of the skeleton. And this is like extremely literally exactly the same as the non-commutative resolution, the quiver presentation that comes from this tilting bundle. And so we just say, oh, hey, look, that is the non-commutative resolution, the kind of most obvious thing you can do with the skeleton, gives you the non-commutative resolution, and you say, hey, look at that, there's an equivalence. All right, and maybe I'll just stop here for now. Are there any questions?
Yes, are there any questions?
May I ask a question?
Sure.
Mhm.
Just
Probably this is this question doesn't make sense, but in the framework of 2D mirror symmetry, does the quantization of the Coulomb branch appear at all?
Not that I know of. It's an interesting question. I mean, so this work of Coulomb goes through doing quantizations in characteristic P. It's like very scary. And one of the things I actually like about this work is it lets you kind of get around that. You never have to worry about that. It's sort of what we're doing is ultimately equivalent to what Coulomb is doing, but we could have just ignored all the characteristic P stuff and did this instead. So like, you know, if you go very carefully read Coulomb's paper and do this quantization in characteristic P and then work out what it gives you, which in this hypertoric case was actually done about 10 years ago by a student of David Nadler's, it just tells you the combinatorial recipe that I wrote before. So there's a paper of Ted Stadnick's that kind of does all of this out. I think he didn't understand the combinatorics as well. So it's sort of not very clear at the end. Like, sort of, it's clear from what he wrote that there must be a tilting generator that's the sum of line bundles, but he didn't really work out what the line bundles were. But, you know, somehow like that shouldn't really be necessary. So yeah, it's an interesting question. I think one of the ways to say that is that, I mean, that quantization should correspond to some structure on the Fukaya side.
Ah, I see.
And it's kind of an interesting question what that is.
Thank you.
I think that's probably the best way to put it.
Thank you for your answer.
Yeah, there are other
May I-
questions? Yes.
Yeah, just may I ask, maybe it's not a very useful question, but somehow in your examples at the beginning, to find a relation, what should be the algebra? Is the algebra very difficult or
No, it's pretty simple. Yeah, I'm sorry, I just things went a bit slower than I was expecting. So anytime there's a hyperplane separating two chambers, you have a arrow back and forth. And then you have a set of relations. So the relations are if there's a codimension 2 thing, going around it the 2 different ways is the same. And then there's sort of a funny quadratic relation, which is if I have a chamber and I look at all the ways of leaving and coming back, then these satisfy the same linear relations as the normal vectors to the faces of the hyperplane.
Mm-hmm.
So, for example, in the T star P2 case, what happens? Well, so you have to remember everything here is periodic. So there's another copy of this blue chamber here and another copy of this blue chamber here. So actually this purple chamber touches the blue chamber along 3 different hyperplanes. It's kind of degenerate. And similarly, the red chamber touches the blue chamber along 5 different hyperplanes. And so along 3 different hyperplanes. So we have, an algebra whose element is the nodes in the quiver correspond to the 3 different chambers. So we have 3 arrows going each way. So this is actually a doubled version of the Bailenson quiver, which would be the quiver that presented just the tilting generator on P2 that you get by restricting this. Doing that sends all the arrows going one way to 0. And, as I say, this is like O of 1.
Oh wait, so
2.
this is also finite dimensional? In this case?
No, it's not finite dimensional. It's finitely many arrows, but there are arbitrarily long paths that have non-zero image.
I see. Okay.
Right, I'm going right. What I'm going to tell. Remember, this is O of 1, O of 2, not on P2, but on T star P2.
Yeah.
And the functions on T star P2 are infinite dimensional. So, these are x0, x1, x2, x0, x1, x2. And I have the usual relations in the Bailenson quiver that say that like x0 times x1 is x1 times x0. And those all come from here. Well, there should be a good explanation of where they come from. I have to think about that. I mean, I think it must be the going this way is the same as going this way. Those are probably hard to see. Like going this way is the same as going this way. And similarly going, right? Because again, remember, you know, this is red, this is red, this is red. And then the maps back the other way, well, they're given by ddx0, ddx1, ddx2, which if you think carefully, you can interpret as sections of O of -1 and T star P2. Right? And the easy way to remember this is that xi ddxi is an actual well-defined vector field. And so dividing that by xi must give you a section of O of -1. And so the interesting quadratic relations, there's only one quadratic relation in this case that comes from the fact that, like here, right, I have, and again, I should just use the, here I have 3 normal vectors, and there's a linear relation between them. And what that linear relation says is that if I look at x0 ddx0 plus x1 ddx1 plus x2 ddx2, that's the generator of the rotation action on every line, which is trivial on T star P2. So as a vector field on P2, that's 0. And that's the quadratic relation.
Right.
Any further questions?
Yeah, I have a question, but maybe just this tilting generator you mentioned. Do you know other places where the tilting generator exists? Like for let's say for a K3 surface?
Well, I can't tell you anything about that because it's not a resolution of something affine. So, you know, somehow Coulomb has this amazing trick for producing tilting generators when you're a symplectic resolution of something affine.
I see.
And it just won't work. I mean, I think it won't work on a K3. I haven't checked myself.
Yeah,
it's an interesting question. Like, it must tell you something about a K. Like,
well,
right,
because
like
I know that this is related to this Gromb-Witten invariance for K3 vanishes. And
yeah. Yeah, short answer is I honestly don't know. I've never actually really thought about what this construction gives you for K3. I sort of only think about these guys that are resolutions of something affine. And but in those cases, whenever you have a symplectic resolution of something affine with this contracting C star action, there's always a tilting generator. It might be very hard to construct, but it always exists.
That's Coulomb theorem. Okay.
Yeah. And I mean, even if you don't have the C star action, you can prove that kind of locally one exists, like locally on the guy you're resolving. Yeah, I mean, sort of the nice thing in this picture, and unfortunately I didn't have any time to say this, for other Coulomb branches, this construction of Stadniks, it actually generalizes. And you can kind of explicitly construct the tilting generators for a larger class of Coulomb branches, with this hypertoric picture kind of being the template, but you get kind of more interesting things from these non-commutative guys. Whereas for these hyperkähler quotients, like as long as they're smooth, they're basically guaranteed to have a tilting generator by this theorem of Coulomb, but it's completely unconstructible. I mean, I shouldn't say that, but it's very hard to construct.
Right.
You know, there are only explicit constructions of it in really special cases. And, you know, somehow like the cases where these guys are, you know, there are certain cases where, like, you know, affine type A quiver varieties can be written also as Coulomb branches. And the Coulomb branch picture explicitly constructs the tilting generator for you. But at least I have no idea how to think about that tilting generator if you wrote it instead as a quotient or thought about it as a Hilbert scheme, like what it has to do with kind of the tautological bundles that come up that way. I really don't know.
Yeah, another question is, you mentioned this T structure from different choice of, is it alpha maybe? Like that.
Yeah.
Do you get a stability condition from this?
So yeah, there's a very nice picture where, you know, so everything is done in terms of these regions. And if you look at the volumes of the regions as you vary the positions of the hyperplanes,
yeah,
that gives you a real variation of stability.
So you do get a Bridgeland stability. Are you talking about Bridgeland?
Yes, but it's a sort of special case of it where everything is only in the real plane. And the way you kind of see the other stability conditions is that when you approach a point where things become singular, which in this picture would be the volume of one of these regions pinches down to 0.
Okay.
You have to check that the order of vanishing of that function matches kind of how much the object shifts in the T structure. So when I hit one of these walls where one of the objects gets crushed down to 0 and a new chamber appears, I actually get a perverse equivalence between the two T structures crossing that wall. So there's this paper of Anno, Mirkovich, and Bezrukovnikov about real variation of stability. And, you know, somehow exactly what's happening there is like, I could kind of go out in the complex world and I kind of know how much my object has to shift because of the fact that it vanishes to order whatever here.
Okay,
Right?
so your answer is more than what I asked. It's basically you know how they change as well, right? How the structure change according to.
It's a story with wall crossing functors.
I think.
So yes, there's a nice story for how to construct these wall crossing functors and the comparing the different T structures.
Okay, very nice.
But one of the things that at least I don't understand very well is like how to think about, you know, sort of you're looking at like a real locus inside the space of stability conditions. And you kind of know implicitly what must be happening when you take a little path through the complex world to get around this wall. But I don't know, like, what does it mean to look at one of these stability conditions where you've gone off the real locus?
Yeah.
And there's sort of this corresponding thing on the Fukaya side, which is these Lagrangian skeletons, which like will kind of, it's exactly kind of a dual story. You're really looking at the volume of components of those as you move these parameters around. And if that volume goes down to 0, well, of course, you could have gone through like sort of a different set of hyperkähler structures where you kind of rotate things a little bit to get around those, but doing that breaks the holomorphicity of the skeleton.
Mm-hmm. Okay, beautiful. Well, are there other questions in the audience? All right, let's thank Professor Webster again. Okay, thank you for the talk, Ben. It's all
right. Thanks. Have a good day, everyone.
Well, good night.
I'm about to go to bed.
Sleep. Yeah, hope to see you later.
Right.
Bye.